Now, before going any farther in terms of the theory of integrating one-forms, let's step back and consider why we're doing this. Why bother integrating one-form fields? Well, there are several concrete physical motivations for working with vector fields and their one-forms. In order to keep this simple and grounded, we're going to work in 2D and consider planar vector fields. In that setting, why would we want to integrate one-form fields? Well, there are lots of instances of wanting to add up direction-dependent values along some path, and all of those convert to one-form field integrals. So, for example, let's say that you have a vector field in the plane that represents forces, and you're walking along a path, and you want to know how much work does that force field do along the path, or how much work do you have to do to overcome that force. That is really a one-form integral. Things change depending on where along the path you are. If we take that same setting and integrate along a loop, then what this is doing is measuring something like how much net spin the vector field imparts along that loop. That is something called circulation, and it's going to be very important for us moving forward. There's a dual problem to that of circulation called flux. Again, if you have a loop, what you might want to do is look at a vector field and say, okay, if that vector field is flowing material, how much material is moving from the inside of my domain to the outside of my domain? Or vice versa, how much stuff is flowing in? Integrating the appropriate one-form field along that loop is going to give us something called net flux. So work, circulation, and flux are going to be our motivations for moving forward with one-form field integrals.